About how to construct probability distributions for equally likely events. So an equally likely event is like flipping a coin twice. In each case, I'm likely to get heads an equal number of times, or 50%. So the probability distribution is going to be the distribution of all possible outcomes of those two tosses. So let's say that I have two flips. Okay, the probability that I'm going to have 0 heads is defined by the probability that I'm going to have tails at flip 1 times the probability that I'm going to have tails at flip 2. So this is just 50% times 50%, which is 25%. The second outcome is that at least one of those throws, I'm going to have 1 head. So this is defined as the probability that I'm going to have heads and then tails, or tails and then heads. And then this is expanded significantly with these expressions. Try not to get too confused about the math here, because the basic idea is that I need to kind of define the probability that I'm going to observe heads and then tails, or tails and then heads. So both of these are defined by 50% times 50%, which is 25%, and 50% times 50%, which is also 25%, which corresponds to at least 50%, or a 50% probability that at least one of my tosses is going to be heads. And then the third outcome that I'm looking for is the probability that both of my flips are going to be heads, in which case I'm looking at the probability that I'm going to have heads at flip 1, defined by 50%, times the probability of heads at flip 2, which is also 50%. Multiplying these two together, I get a 25% probability. So this is a probability distribution of the likelihoods of arriving at heads across two different flips of a coin. Okay? So in the one case, I have a 25% probability that I'm going to receive no heads across the two flips. I have a 50% probability that at least one of the tosses is going to be heads, and I have a 25% probability that both coins are going to land on heads. Now, I also want to construct a probability distribution for events that are not equally likely. So in the criminal justice field, for example, in precincts that have homicides, they have certain clearance rates defined by their past experiences. So let's say, for example, that a given precinct has a clearance rate of 60%, or 0.6. That tells me that the probability of a non-clearance is 0.4. So table 5.2 provides all possible combinations of these results. So in any 3 homicide cases, I'm likely to have 3 non-compliance. I might have the first comply and the second 2 not comply. I might have the first non-comply, the second comply, and the third non-comply. All of these are defined by this same multiplicative rule. So in each case, if I have non-compliance, 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 it's the probability that it's going to be non-compliant 3 times. So 0.4 times 0.4 times 0.4 means that I can be 6%. It's 6% likely that any 3 are going to be non-compliant. And so along this way, we can solve for probabilities of all of these different combinations across these various options. I want to speak briefly about the difference between a frequency distribution and a probability distribution. A frequency distribution refers to what was observed, whereas a probability distribution refers to what we could expect should happen. So let's go back to the probability distribution of hypothetical coin tosses. This is what we would observe theoretically. Okay? But if I want to know what I actually do observe, let's look at this. This is a frequency distribution of 10 flips of 2 coins. Okay? And what I want to do now is not solve for the probability that I would observe 0 heads. Instead, I just want to record across my 10 flips of these 2 coins on how many of those trials did I observe 0 heads. So here I have the outcome, 0 heads, and I have a frequency of 3. That tells me that 30% of the time I flipped 2 coins and got 0 heads on both coins. Likewise, across those 10 flips of 2 coins, I had 6 cases in which one of the coins landed on heads, and that corresponds to 60%. So we can see here the difference between the probability distribution, which we would expect due to theoretical equally likely events, versus the frequency distribution, which refers to events that we actually observed.